So as promised, we're going to continue our discussion of how to take the idea of flows as a tool to solve problems that may or may not have anything to do with flows just by the surface. Right? And again, this will be sort of a good warm-up for the more general idea of how you can take problems and frame them in a linear programming or convex programming setting. So it gives you a bit of practice in how these things work. What I want to remind you of is that when we take a problem and want to sort of put it into a flow setting, we have this almost like a language translation. We have to express the concepts in our problem in the language of flows. This also comes up in anti-completeness reductions that we will cover later on, where you have to express the concepts of one setting in the concepts of another setting. And again, the concepts of a flow problem are what? We have edges plus capacities. We have a source and a sink, and the idea of flow, and also the idea of a cut. Right? And it's important to keep in mind. We're going to look at two examples today, or we'll see how far we can get to them, where, in one case you have to think of trying to find a flow, in the other case you have to think of trying to find a cut. And of course we know they're both the same thing, but it's helpful to model it this way. And again, there's no sort of formula for how to do this, but generally speaking, you can think of flow as a choice, right? You're searching for ways to assign values to edges, especially if your edges have 0, 1 capacities. Assigning a flow means either you're picking the edge or not, right? So if you have a capacity of 1, either you push a flow on that edge or you don't push a flow on that edge. So it's like a binary choice. So whenever you have to make choices about things, you can think of, okay, maybe this means I need an edge to capture something, and that edge should have capacity 1, so either I pick or I don't pick. Again, this is a rule of thumb. It's not a formal. It's not a formula. Similarly, if your goal is to find, I want to find a subset of things that has a nice property, right? Well, flows don't give you a subset, but a cut does. Sometimes you can think, okay, I want to find a subset, so I need to formulate this in the language of a cut, and then do things like that. So we'll see examples of both of these things today. But that's something you have to keep in mind as you try to take your problem, like the assignment that you're going to get next, you're going to have to take a problem and map it to a flow problem. These are the ways in which you can try to attack the problem. Okay, so without further ado, let's look at a problem. And all of these, there are notes, the Jefferson note has both of these examples, and I'll point to exactly where to go look for. So don't worry if you're having a hard time writing things down. So the first problem is a sports example. And it's for those of you who follow sports, this is a common thing. You're midway through the season. Let's see, where are we now? We are now in March. Okay, so the NBA season is kind of midway through. People are beginning to think about playoffs. We're not quite there yet. There's still hope. Your favorite team, there's still maybe have some hope of getting into the playoffs. And then you're thinking, okay, what chance does my team have of making the playoffs? And then of course, commentators love to say things like so and so has been mathematically eliminated from the playoffs. I don't know if they know what they're talking about. They say that, but we are going to know what we're talking about because we're going to try and figure out today what it means to say you're mathematically eliminated from contention, right? And so we're going to take a simple version of this problem. And in all of these settings, you have a bunch of teams. So you have teams, A, B, C, D, E, right? And you have your favorite team, which is of course the best team, the team that gets all the bad calls from the refs, the team that has all the best underappreciated players that you want to make the playoffs. Right? And all these teams have played some games, they've won some, they've lost some, and they're all going to play each other. We'll keep it simple, we're just assuming they're all playing each other. So if you don't like NBA, you can think of the IPL, which is the Premier Cricket League, which is going to start, March 19th? Anyone knows? April 2nd, okay, there you go. And so every team plays every other team, so we'll keep it simple that way. And now, you have to know, depending on who plays who and who wins what, will your team make it, right? And the way we'll define your team making it, because it's a competitive league, is no other team gets more wins than your team at the end whenever all the dust settles. So maybe only one team is going to qualify from this group, right? And you want to make sure it's your team. So you want to see, does your team have a chance? Can fate arrange itself in such a way that your team will actually make it? So in particular, we'll assume that every team, right, has some set of wins. So every team has some wins already, right? And there is a table saying, okay, team I will play team J 3 more times, or team J will play team K 2 more times. So there's some kind of matrix that tells you I will play J Gij times. Okay? We'll assume there are no ties. My team either wins or loses. Okay? A choice. And we are focused on our team. We want to know if our team will make it to the playoffs. And making it to the playoffs means, will A qualify? Which means that at the end, the total wins of A should be greater than, so let's assume that it should be greater than or equal to, let's keep it greater than or equal to the total wins of all other teams. Oh, total of any other team, sorry. Okay? Oh, sorry. Okay. I'll give you 5 minutes. Your goal, how would you, if possible, put this in the context of a flow computation? And I'll even tell you it's a flow computation. So your goal is to come up with a graph, come up with edges, directions for the edges, capacities for the edges, sources and sinks, and some condition on the resulting flow. So there's no maximization here. So you're not trying to create a max flow. What you will ask for is, is there a flow that has some property to it? And we saw this example last time as well, right? In the case of matching, is there a flow that saturates all the edges coming from the source? That's the kind of thing you might want to see. How would you do that? Okay, so think for a moment. Yes, clarification.
Any other team or like within a group?
This is a group. Think of this as a group. So your universe is just a set of teams.
So total of 4 teams would be getting qualified.
Pardon me?
Total of 4 teams would be getting qualified from in this case, because you said.
Yeah. I mean, here's what it is. Yes, they're all, they have too much money. They buy all this kind of stuff. Our team, we really work hard. Okay. I'm just going to leave this off while you're thinking. If you know what the problem is, because my iPad battery is draining rapidly. I want to make sure I have enough to survive till the end. Huh? Do you have a USB-C? That's the problem. I had a charger in my office. I forgot to bring an extra card. Actually, can you go to my office? You know what the iPad charger looks like? If you go to my office, where the plugs are underneath my desk, there's a white rectangular plug. Okay, so what I'd like to hear from you, again, are not answers, but I'd like to hear, really more about where you feel like you're getting stuck. Like where your impasse is when you first start thinking about this. I think that's more important than knowing the answer. So I would like people to share with me where they feel like they're first getting stuck. I don't know what projects. Okay.
Like expressing this thing like total wins of A is greater than equal to total wins of any other team. Like
Yeah.
They find this to be
Difficult
difficult
to capture. Right. Okay. Another way of saying this is that total wins of any other team has to be less than equal to total wins of A. I'm not totally joking here. What I mean is, this is a greater than equal to constraint. If we flip this around, we have less than equal to constraint. There are less than equal to constraints inside a flow formulation. Where are they? Where do you see a less than equal to constraint show up inside a flow formulation?
Mass flow.
Sorry?
The mass flow.
The mass flow is an equality constraint, right? Flow coming in has to be equal to flow coming out.
The lower bound, right? We have
A lower bound is greater than equal to constraint.
Capacity.
Can I say more?
That's all I got. It's just
But you said something. So-
capacity.
But what about it? What about capacity?
It's a less than or equal to.
Flow has to be less than equal to capacity. So, okay, you have a greater than equal to constraint. You flip it around, you have a less than equal to constraint. We know there's a less than equal to constraint somewhere in flows. Maybe that's somewhere else. Okay, so that's the first thing. What other obstacles do people feel like they're facing as they try to formulate this? Yeah.
So if you're considering this as a flow problem, then what is the source and what is the sink?
You're struggling. So what I would suggest is in that kind of situation, don't worry about the source and sink just yet. Try to set up the graph, and often the source and sink will become clear as you go along. So let that not be the first thing you do. Try to think of how do I encode notions of winning and losing and stuff like that. That's what it is. Okay, so that's another suggestion I would make. What else? Yay. It's charging good. Okay, what else? What other obstacles do people? These are good questions. These are exactly the kinds of questions you should be pondering and getting stuck on as you get to. What else? Yeah.
how to construct the graph appropriately.
Pardon me?
Or how to construct the graph that represents this, structure of winning and losing.
Okay, let's be more specific though. That's a general question. How do you construct the graph, right? But in this context, what is the problem you're facing?
We're trying to, figure out.
So another way to say this is, what should the vertices and the edges of this graph represent? Right? There's some kind of magic flow graph, right? It has to have vertices and edges. Vertices have to capture something, edges have to capture something. What should that be? Right, so that's the issue. So that's almost the first challenge you face, right? How do you translate that to this? What are the choices you're making here? In other words, the system is going to search for something. It's looking for a possibility, right? Like a way for your team to survive. What choices does your system have to make? What does it have to decide on?
If you're winning, you should follow one path, and that should be different from when you're losing.
So winning is one path, losing is another path.
And
Okay.
yeah, we should get all the options. Like if you win the first game, we should still be able to connect the remaining winning graph, and that's.
Does it matter what order you win the game?
No.
Good. So that's a good thing to remember. What really matters?
The number of wins and the number of.
Good. And you have to decide which game gets won, which game is lost. So there's a choice that encodes winning and losing. And remember, we said choices might be something that you decide to put flow on edges. So maybe a flow on a particular edge is a win, and a flow on a different edge is a loss. Right? Okay. If that's the case, what would the vertices be?
Just binary, like 1 and 0, would that be? I'm not sure. But just two numbers will be enough to represent all the vertices.
Right. So one thing you might think of, okay, I have one vertex for each team. Right? That would be a natural thing to do. And I have an edge between them. And now I want to use that to encode wins and losses somehow. Is that how people are thinking? Yeah? You were going to say something?
So which we have in the residual graph.
Sorry?
In the residual graph.
Oh, you want to use a residual graph. So an edge from this is a win, this is a loss. Okay. So in other words, you want to somehow say something like, if I have team I and team J, this is the number of places where I beats J, and this is the number of places where J beats I. Is that what you're saying? Roughly? So the total flow would be W minus W prime. Maybe, yeah.
But in this case, we also want to make sure that W plus W dash is less than equal to total number of games that are played between.
Okay, good. So maybe we need to do something like, maybe we need to rewrite this as like this edge from here to here has capacity equal to G I comma J, right? And so obviously you can't have one team winning more than that, right? Okay, so this is basically saying how many games. This is like encoding the number of games in which I beats J. Okay, good. So the number of games in which I beats J, that's fine. What else do we need? So we're getting somewhere now, right? We've got something going. Now what? Now we need to know the total number of games that I wins, right? Because we have our team, we want to make sure that our team has more. So how would we do that? So these are the, so in other words, if we think of I going to J, that's the number of games in which I beats J. We can also think of this like this, right? So we have I to K, I to L. The total amount of flow going out of I is how many? Is the total number of games that I has won. Okay, that's helpful, maybe. What can we do with that information?
If we disconnect I, that should be the max cut.
More words.
If we cut from the edges related to I, and if the cost is greater, then
Okay, the flow is great.
if the flow is greater than this cut flow of any other vertex, it's like.
Except that, how do we express that in the language of flow? That's the challenge, right? So that's our feeling right now. Okay, maybe you want to look at the flow coming out of I, and that somehow has to be. If I is not our favorite team, then that flow coming out of I should be less than the flow coming out of our favorite team. But we don't know how to do that. That's kind of weird. You had a comment?
So exactly that. So you just some values that go out of I, and then compare it with all the other vertices that are not I.
Right. So our challenge right now is that you've correctly zoned in on the issue. We need to somehow have a way to encode the amount of flow coming out of a vertex. But in this framework, there is no explicit way. It's merely the sum of all these edges. We don't have an explicit way of doing this. Suppose we had a way to kind of flow everything coming out of this vertex as a single edge coming out of it. Then we'd know exactly how much there is. But in this language, we don't. And that seems to be a challenge now. How do we set things up so that the number of wins by a team corresponds to the amount of flow coming out of it? If we can do that, then it seems like life might be better for us. Right? So for example, again, let's just sort of go a little crazy here. Let's pretend everything else is figured out. And now for every vertex, we know the amount of flow coming out of it. So this is the number of wins of that team. Right? If I tell you this, can I now express the constraint, can I express the desire that I want my team to have more flow? So one simplifying assumption we can make is like we are optimistic about our team. Our team realizes what a dire situation they're in. They're going to practice every day. They're going to summon all their spiritual energies and do all the superstitious things they do to win. And they're going to win every single game. Okay, forget the other stuff. But they're going to win every single game. If our team wins every single game, how many wins will they have at the end of the season? Well, we know this for sure. From the input, we know that if our team, let's say our team is team one, right? So our team is team one. Their total number of wins at the end of the season, if they win every game, because they don't, there are a bunch of losers, they deserve to get into the playoffs anyway. So it's W1 plus summation G1 comma J for all J. Right? This you know at the time of input. This is the maximum number of wins our team can make. One is the total. One is our team. W1 is the total number of wins we have so far. Also, where it's an intermediate point in the season. Okay. Right? So this is the total number of wins we can have, maximum number of wins we can have at the end of the season. And let's assume we win all our games. Right? Okay. So if we win all our games, then this is our maximum. Let's call this maximum, I don't know, M1. Okay? So now we know that the total flow for every other team has to be less than equal to M1. Right? I've also said, let's assume I can figure out a way to get a situation where the flow coming out of a vertex is the number of wins that team has. Then what should I do?
This entire term in M1, like W1 plus G.
Yes, so this I know at the time of input. I don't have to do any work. This I can just look at my input and figure this out, right? This is just a summation. So then how should I set up my flow network now, knowing M1 and assuming that I can do this? Not the whole network, just this part of the network. So somehow magically someone has figured out a way for me to get to this point. Now what do I do? Yeah?
Could you set up a sink and then have the total flow into the sink be the remaining games from all the teams?
How would I encode this M1 constraint in? But I like your sink idea. So maybe what we do is we put all these teams have an edge going out to some big sink, and the capacity of those edges
Should be M1 minus the WI or whatever.
should be M1 minus W1. The remaining number of wins of each team is not allowed to be any more than M1 minus WI. So now we're getting somewhere. You don't look happy. Are you happy? Because this is exactly what you were suggesting. We need somehow a way of capturing this thing.
M1 is the max of the first team?
Of our team. Our team, not the first team. Our team.
Okay.
Our hometown.
So max is the total number of wins it could.
Our team could make if they win every single game.
Okay, max.
Yeah. So we're making a simplifying assumption. I should have mentioned this earlier, but we can make a simple. Let's assume our team wins all those games. Then can it make the playoffs? Right. So now, if we can set up the situation and put this constraint, then the total number of wins of any other team, by design, will not be more than this. Now we don't know if the situation can occur, but this is the constraints. We're saying, is there a world, where this could happen? That's what it means to be mathematically non-eliminated. Right? So now the question is, how do we achieve the goal of having the flow coming out of this vertex for this team be the total number of wins it gives?
Should it be strictly less than M1 minus WI? Because if it were like less than.
So in my specification, I said let it be less than equal to. But you're right. If you want to make it strictly less than, what do you do? Because you either win a game or lose a game. We're not half points. We're not doing World Cup song. Okay. So we've solved half the problem. Right? If we were able to somehow encode the number of wins as a team as a flow coming out of it, we're done. How do we encode the number of wins for a team as a flow coming out of it? Well, obviously it has to be the total flow coming into it has to be the total number of wins. Okay, so that's something. Anyone? How could we encode the flow? It doesn't have to be a single edge, it could be multiple edges coming in.
Probably for all the teams it is playing with, we can have an edge and then
So now we've already created a vertex for each team. Are we going to use that same thing here, or are we going to create some different kind of vertices? So you could just add an edge from here to here. That's going to mess up this whole nice thing we've set up. So maybe we should do it slightly differently. So here's one idea. One idea is, okay, let's set up another vertex for all games between I and J. So for every pair I and J, I have a vertex. This represents the rivalry between I and J.
that would just be unique games, right? Each game is
No, this node represents all the games between I and J. right? And we're going to use one edge that points to I and one edge that points to J. And what is that flow going to represent? The number of games that I wins, the number of games that J wins. But there has to be some constraint. We can't have them winning all possible games. What's the constraint? How much flow can come into that? The total number of games possible. So the capacity here is equal to G I comma J. So this is kind of what we were getting at originally, right? That idea was a good idea, but it needs some tweaking. This idea we had here with an edge. So we're kind of modifying it a little bit to make it look like this. Now, what should the capacity of these edges be? Of these two? Does it matter? No, doesn't matter. Why doesn't it matter?
They are not related.
They're not related, but does it matter? But do we need to constrain the capacities? Okay, let me ask the question this way. If we constrain the capacities on these edges, what does that say about the original problem? It's saying we're limiting the number of wins I can have, or the number of wins J can have. So there's a natural limit then, which is Gij. Another way of saying this is we don't care because only Gij flow can come in E. So it doesn't really matter. So you could put it as infinity, or you could put it as Gij, which effectively is infinity. So this could be, let's say, okay? And now, where's the source? Where would the source be? It's kind of the clues in the drawing. Right? So you can think of the source as pushing out games to the pair all the different rivalries. And the flow computation is magically deciding who wins what. Right? And now we're asking, is there, so now notice that all these edges represent unique games, right? Games between I and J are different from games between I and K, from L and J, and so on. So each unit of flow represents some game, right? So the total flow here is the total number of games that are played. Now obviously you want to play all games, so you want to push all flow possible, right? So the question is, if you push all flow possible, then the max flow that you can push is all the games. But now when you push all the flow for all the games, you have these constraints now. You have this capacity constraints on those things, right? So your flow procedure has to figure out if there's a way to arrange all the wins and losses so that no team wins too much. But that's the flow's problem. It's not our problem. In other words, our question now is, does there exist a max flow of value equal to the sum of all the games? So our claim is now, our final reduction is, to solve the problem of deciding whether my team can make the playoffs, I construct this flow network, and I run my max flow, and I ask if there in fact is a flow that saturates all the edges coming from the source. Because instead of saying, okay, find the best flow and see if my team survives, you're saying, look, I want to make sure my team survives. Is there any way this can happen? If it turns out that the solution, so let me stop for a second. So this is the algorithm. We now have to prove that this is a correct reduction. Okay. Suppose there is a way for my team to win, make the playoffs. Is there a flow solution here? If there is a way for my team to win, then there is results for all the games that make sure my team wins, that does not have fewer wins than any of the other teams. I merely assign all those wins appropriately to each of those edges as flows. All the games are played, all the wins are assigned, and we know that no team has more wins than my team. Therefore, because I've chosen M1 minus Wi, I've accounted for this. So if my team can win, there is a flow network here that satisfies the constraints of all the edges being saturated. Suppose all the edges are saturated here. Well, that means that if all edges are saturated, we now have an assignment of wins to each team, so that no team wins more, and that should be that's the world I will now live in and watch and wait every day to see, does that follow that? So if there's a solution to the original problem, there's a solution here. If there's a solution here, there's a solution to the original problem. I have a reduction. My problem is solved. So do you see all the steps in the process? You take the problem, you do all the work, the hard work of trying to model your problem in the flow network, then you prove A implies B, B implies A. But you had to specify something very key, right? It's not just that, oh, here's a flow network and I'm done. It's more like, here is a flow network, and I will run a max flow and check if the flow saturates all the edges from the source. If that's the case, then my team, and you have to specify what the reduction is. Right? You have to say what it means to say I run the flow and how does it give me an answer for my original problem. That's also part of my algorithm spec. And then you can prove that it's correct. You can't just say run a flow. Well, okay, fine, but then what? That's not enough here. For example, if I ran a flow and my flow did not saturate all these edges, that means there actually was no way to do this. So you have to say that. Okay, any questions? This is going to be the template you will use for pretty much probably all the questions in the next homework. I'll give you a problem and I'll say solve it using flows, and you'll have to do a template like this. So this is a good time to ask me some questions about how this process works. Yes?
I don't know, I mean, initially I was a little skeptical about like using your team as a vertex. Rather, I thought we would use the games as the vertices.
Which you're doing now.
Which we're doing now. But ultimately, do we also like always end up using what is in the input as like the final vertices? Like
Well, I don't know what that means. We are using what's
the
in
teams and the games, both we are using here.
Depends on the
And
problem, right?
Can it be modeled differently also?
I'm sure it could. They're usually that I don't not say this unique answer, but I'm more concerned about how you get to this answer than getting the answer. Right? So this thinking process that you all went through, the obvious solution for this, right, or at least the seemingly obvious thing, is put one vertex per team and put an edge between them. And you have to go through that first to realize that there are some issues with it, because you can't encode everything you want. Which then tells you, okay, maybe I need to change it a little bit. So you get to this partial solution here. Say, okay, well, I need to get something to get that. Okay, then I need to get this. You never get a solution in one shot, right? You always this partial, this slowly refining until you get it. And I want to show you that process. So, I mean, yes, there may be another way of doing this. I don't know. This is the way that sort of is, I wouldn't even say most natural, but this is one way that works. But I will not expect a single answer. I just expect an answer that's correct.
So these vertices in the middle, they also contain vertices like K, J or something, right?
For every pair, well, they'll contain for every pair of teams that actually has games with each other left. Yes. Yeah. Notice that all of this works only for one team, right? If you want to know which teams will survive, you have to do this over and over again for each team. This is another story there. In fact, someone showed that you can do this with one flow for all teams. But that's a different story altogether. Yeah.
Could you explain again why you have the infinity flow from ij to I or j? Because number of win I, win j or j should be less than g I j.
Yeah. So I mean, you're right that technically I should put it as Gij, but I also want to point out that even if you made it infinite, the total amount of flow that can come in there is only Gij, because that edge has one thing coming in and two things coming out. So functionally, it does not matter. Again, in the linear programming language, you're saying that variable is unconstrained, which sometimes can be good, sometimes not. So I'm saying both of these are acceptable. If you put infinity, you have to say why infinity is okay. If you put Gij, you don't have to say it. But you still have to argue that Gij is the right number, because you're saying the maximum number of wins of any one team is Gij, therefore it should be Gij. So my instinct is just, okay, we'll put infinity, but you can also, Gij is fine. But infinity is not wrong in this case. It's not wrong because there's only Gij flow coming in anyway. What do you do? You don't have negative flow. Okay. Next problem. Here's the game. And this will be familiar to anyone who's ever had to install software until the next version of their Mac. I have, well, let's just say, I have projects. This is a project. Okay? The project has some value for completion. Okay? So I'll call it project B, that's some value. The value can be both positive or negative. If the value is positive, I got some profit from it. If the value is negative, I have to pay some penalty. Okay. I have lots of projects. There's a whole bunch of them. And the catch is that some projects require other projects. If you're installing software, you know that if you install one package, you need more. You wait for 3 hours to curse your life and you curse the whole computer side. Maybe it's just there are dependencies in your system. So I give you projects, I give you profits for projects or values for them, which could be positive or negative, and I have dependencies. This dependency basically means V has to be done before you can do E. That's the way it is. My goal execute a set of projects of maximum total value, while keeping in mind all the dependencies. Okay? So it's a selection problem. I'm not going to execute all the projects, only some of them. Right? And I would like to choose all the ones that have high value. But obviously, since things depend on other things, the things that I might get high value, but all the things I depend on might have negative value. So actually, my net value may not be that great. But it's not even just that; they could depend on other things. So it's complicated very quickly, right? But I want to choose a set of projects that has maximum value. So I'm going to select some subset of these, while keeping in mind all the dependency constraints. And I want to solve this using a float. And the first thing, like I said earlier, was since I'm selecting a subset, that sounds more like a cut than a float. So this is going to be a little different from the previous problem, where there I was thinking of edge flows and choosing. Here, the things I'm choosing are vertices. In fact, I already have directed edges, so there's already a bit of a clue as to what things might look like. The main challenge is to set this up as a min cut problem. Yeah?
So why aren't you doing all the projects?
Is it clear that doing all the projects has maximum value? Because remember, some projects should have negative value.
Oh, sorry. Okay.
So I'd like to avoid things of negative value. Like anything, installing any package that involves JPEGs and stuff can often be very painful. If I can avoid things that I'd like to avoid doing. Okay. We don't have much time left in the class today, so how about you think about this for a few minutes and then we'll just talk it out. I'm not going to solve it today, but we'll just talk out where we are stuck. Because this is again different. Right? So the trick here is going to be to think about how to set up your capacities right, so that your cut captures some kind of sense of value. And I already have edges between things. So essentially all you need to do is see if there are any other vertices needed and where your source and sink need to go and what capacity. Okay. Let's think for a bit. Again, we don't want answers, we just want where is the first roadblock you're making.
assign the edges between various vertices as the capacity of 1, and whenever a flow will flow through that edge, it means that both the vertices are in a set. And if there is a zero flow through them, it means that the U vertices will not be selected, and then keep on doing it.
So add a capacity of 1 to
add a capacity of 1 to each dependency.
each dependency.
Yeah. So whenever there is a flow flowing through that edge, it means that both the vertices are going to be in our solution. If there is no flow flowing through it, then U won't be selected, and whether V will be selected is decided based on whether there is an edge coming out of V.
Suppose your thing looks like this. If I only have 1 unit of flow going from U to V, how am I going to make sure I capture everything that has to go? So again, I'm not saying this to say that you're wrong. It's just that this is how you would want to think about what would happen next with your idea. I'm not saying your idea is broken, but it needs to address this issue somehow. And again, what I would suggest is, at least for this particular question, try not to think about flows. You try to capture a big cut, which is a much more static object. So the way you encode is should be in terms of capacities, not in terms of flow, because you're trying to do selection. So this is a little weird. I just spent 25 minutes telling you to think about flows. But I'm also telling you now, for this problem, because you're doing subset selection, it's kind of more like a cut problem. So you're going to get used to the other way of thinking as well. So just, yeah.
Good. Thank you.
We only have 2 minutes to go. But thank you for all being so nice about it.
Well, since the projects are just ordered, that means if you
Are they ordered?
Well, they're
Partially ordered.
One goes first.
Partially ordered.
If you did V and V was connected to a bunch of other projects, you could do all of those projects.
I have to do all those.
You have to.
Right, because that's what it means, right? In order, an edge from U to V means in order to do U, you have to do V. An edge from V to something else means in order to V, you have to do that. In order to do V, you have to do that. In order to do V, you have to do that. In order to V, you have to do that.
Oh, I guess I was thinking about it.
And then or, no, yeah. The edge, yeah, it's a bit non-intuitive, right? You're right. But the dependency means that has to be done first and then I get to be done next.
Okay.
Because this depends on that. Yeah, your comment.
I was just thinking, what if, first we reverse, we get directions opposite to the dependency.
So you reverse all the edges.
Yes, and then we assign them values. For example, if you had an incoming value of all the projects before it to be, for example, 25, I add that value to the edge which is going in between U and V. I mean, I'm not sure, but I was thinking in that direction so that ultimately, when we are at the final, when we finally end traversing, we'll have a sum of all the values that came from that part.
How is this a flow problem or a cut problem? And again, remember, I'm trying to limit your creativity by saying I want you to put this into the language of a cut or a flow. I'm not asking you to solve the problem. I'm saying solve the problem using only this way. I mean, it is fairly entertaining. I was just thinking about this while I was waiting for you. If you had to come up with a greedy solution, what it would look like. And that would look a lot like similar to what you're suggesting, but that's fine, but that's not what I'm asking for right now. Okay, so anyway, we'll talk about this more, but think about this. Again, the trick here is going to be to think about how to think about this way. You have to, if you're trying to capture maximum value of a subset, what you need to do is somehow encode the value for any subset you pick in terms of a cut. But you also have to flip things around because I want to do a min cut, but I want to maximize value. So somehow you have to set things up so that the value, the profit, is something that is, something minus the value of a cut. So by minimizing the cut, you maximize the value. So your first goal should be for any subset I pick, not even the best one, any subset, even one vertex, right? How do I capture its value? And how do I incorporate the idea of a constraint? And intuitively, what you want to do is say something like, if I don't pick all the dependencies, its value should be very small, like minus infinity or something really terrible, so you'll never pick it. Okay? So you have to somehow encode the idea that not satisfying the constraints really drops your cost down a lot, really drops your value down a huge amount. And among the things that don't have a bad value, the value of a subset is somehow related to some cut related. That's how you need to think about this. This is not a solution again, but this is a solution concept, right? An idea for where you're going to approach. So think about that, and we'll reconvene on Friday.